NR, 2 to the minus n, mutual information, minus 3 epsilon, minus a term that vanishes as n goes to infinity. So minus 1, which is just, in fact, because this is less than or equal to, I can just drop that because it's positive. But the effect of that minus 1 will vanish because as n goes to infinity, that goes to 0. Which is equal to 2 to the minus n, mutual information, minus nr, minus 3 epsilon. Okay, bearing in mind that epsilon can be chosen as small as we want, what is the criterion for this to go to 0? This goes to 0 as n goes to infinity, so long as, excuse me, I took the n out here, so that's minus r. So long as what? As n goes to infinity, I want this to be positive. As long as that's positive, this will go, as long as that's positive, n times a positive number will go to infinity. So 2 to the minus n times a positive number will go to 0. And that's an upper bound on this probability. So, what do I want?
It must be less than the division.
Exactly. So the interpretation is that this is the probability of, this is basically the probability of confusing two code words. In other words, that's the probability that the probability of being in T1 complement is basically 0, so we can forget about that. So this is basically the probability that that any two code words, or excuse me, that more than one code word will be jointly typical with the original. So as long as there are sufficiently few code words, this overall probability will still go to 0. So in other words, this is the individual probability for each code word, and we multiply that by the number of code words. So as long as the number of code words is sufficiently small, I should be able to distinguish any two code words with high probability, and that's what this is telling me. So in other words, the rate just has to be less than the mutual information. Yes?
At the point where you made the assumption, or you resembled the x and y variables to tilde variables, there you're checking what happens if suddenly there is a mismatch between input and output.
Yes. Well, it's better to think of it this way. So
normally they are dependent, but
yes.
you assume that, let's assume they behave independently, then what would be the boundary case?
Precisely. So it's also good to think of it this way: is that I have an observation, and I'm trying to match it to randomly selected inputs. So what exactly one of those inputs will be dependent with the output. The rest are independent with the output, even though they're all identically distributed. So what I'm asking is, what's the probability that any one of those independently selected inputs will also be jointly typical? So that's what's going on here. Okay, so that is the big story. As long as rate's less than mutual information, this probability goes to 0. So in other words, average probability of error, the average probability of error over all possible code books goes to 0. Now, we're not done yet, because what we promised was that worst case probability of error goes to 0. We also haven't said anything about capacity. We've just gone as far as mutual information. finish up, have to take care of three issues. Firstly, let C be the max over all possible input distributions of the mutual information. So when we specified the random code book, we did not specify the input distribution, but that was the only parameter governing how that code book was selected. In other words, the probability of each individual element being 1 or 0. So what we can do is we can maximize that over C, and then so long as the random code book is selected with P star of X, maximizing, let's call this equation star, maximizing star, then I can achieve rates are less than C. So in other words, I can do anything up to mutual information, but then the trick is making mutual information as large as possible. And C is the largest possible value for mutual information. So C is the capacity, which is the largest thing I can do with mutual information. Okay, now we get into worst case. Secondly, since the average probability is the average probability of over all code words in code books goes to 0 as n goes to infinity. Since the average goes to 0, I mean, I'm not saying that there are no bad code books. In fact, we can easily think of a bad code book, which is the entire code book is filled with zeros, which is possible. But the average code probability where it goes to 0, there must be at least one specific code book C star with the probability of error, given that C star is the code book, goes to 0. So that's just the mean value theorem. If something is the average, then there must be at least one element that's less than the average. Less than or equal to the average. Okay, so now the idea is we have to get rid of all the bad code words.